Hello class, we're going to do Notes 15.2, starting off with a quick little definition that you should be familiar with, and that is the derivative function is a slope function. The input is a point, and the output will always be the slope of the curve at that particular point. Why is that important? Because no matter what the notation, whether it's function notation, parametric, vectors, polar, the slope of the curve will always be dy dx, the change in y divided by the change in x, which of course is the old middle school definition of rise over run. That is always going to be our slope. So yes, we're having a unit on parametrics, but dy dx, rise over run, is still going to be the definition of our slope and the way we're going to calculate slope. So if we have our parametric functions, x of t and y of t, in our parametric relation, then our dy dx, if you recall from our differential equations that we've taken the derivative of, since y is a function of t and x is a function of t, when we take the derivatives, we'll take the derivative of y with respect to t divided by the derivative of x with respect to t, or just y prime of t divided by x prime of t. That's how we'll find dy dx. Because again, when we do this, we have to remember that this slope function is not a function of x, it is a function of t. So good old chain rule will apply here. Given a parametric relation defined by x of t and y of t, we're going to go ahead and go back to our tangent line equation that we did a long time ago. You can see the definition of our tangent line equation is y equals f prime of a times the quantity of x minus a plus y. In this notation, in parametric notation, we can think of this as dy dx at t equals a, which would be x minus x of a plus y of a. And just another way of writing the same thing, this dx, or excuse me, dy dx at t equals a can also be written y prime of a divided by x prime of a. So this, when we're asked to find the equation of a tangent line, we can think of this equation in our parametric curves, or on our parametric curves. Okay. Quick note, there will be a need to check that at t equals a, that both of these exist before we write that equation. So please check those as you do your problems. Now I've got a little table here I'd like to go over just to kind of summarize our horizontal and vertical tangents. Remember, those were pretty important things that we needed to check and use accordingly. So let's first of all look at our horizontal tangents. Horizontal tangents, of course, occur at some point here when our curve becomes horizontal. And, of course, that's when f prime of x equals 0. There's no change in y. We have no rise and a rise over run. So that's going to occur when dy dx equals 0. If you recall up here, dy dx can be written as y prime of t divided by x prime of t. So when this equals 0, the numerator, y prime of t equals 0, or dy dt equals 0. You'll see there's a note of one exception, which I'll talk about in a moment. But let's go ahead and take a look at our vertical tangents. Vertical tangents, of course, occur when we're on our curve and the curve goes vertical. That's when f prime of x does not exist. or also another way of thinking about that, that's when there's no change in the x. So this is when dy dx does not exist, or x prime of t equals 0. Back up here again, we're looking at the denominator. Denominator equals 0. This does not exist. dx dt equals 0. You can see in vertical tangent, there's also a note that there is one exception. So let's take a look at that exception. An exception occurs, we are not going to be horizontal or vertical, when both x prime of a and y prime of a at the same time or simultaneously are 0. In this case, the particle is at rest. The particle usually changes direction at this time, and usually that's where a cusp will occur, when both x prime of a and y prime of a are both 0. We're not going to be horizontal, we're not going to be vertical, there's going to be something else going on that we'll have to take another look at, or look at a little bit closer. Let's do a problem. Our first example says that x is defined as this function here. You can see we can easily take a derivative of that with respect to t and get -2 cosine of t. Our y function is defined by this. We'll take the derivative of that with respect to t and get 2 sine of t. So to find our slope, or our derivative function, dy dx, we're just going to take the dy dt, or y prime of t, and put that in the numerator. Our denominator will be the x prime of t, dx dt, which is -2 cosine of t, which simplifies to negative tangent of t. On our next problem, it asks us to have a function defined in the x direction by this, in the y direction by that, and find the slope of the tangent line at this particular point. We first take the derivative of x with respect to t and get 10t minus 7. Take the derivative of y with respect to t, get t squared plus 6. Next, we just put the y prime in the numerator, x prime in the denominator to get our dy dx. No need to simplify that one. And so we can take that equation and substitute in t equals 2 and evaluate dy dx at t equals 2. We'll get 2 squared plus 6, 10 times 2 minus 7, which would give us 10/13. So the slope of the tangent line when t equals 2 will be 10/13. Number 10 has a parametric equation defined as follows. X is 3 cosine of t, y is 2 sine of t, and now we're asked to write the equation of the tangent line at t equals 1/6 of pi, which of course this is going to be our a value in our general equation. So you see the first thing we do is go ahead and take the derivative of x with respect to t and get -3 sine of t. Derivative of y with respect to t gives us 2 cosine of t. Write this as a fraction with the y prime over x prime. A little simplifying gives us -2/3. Cosine over sine is cotangent of t. Next, in order to write our tangent line equation, we need to evaluate 3 things here. We need to evaluate our slope at that point, pi over 6. So I went ahead and used my cosine, since those are the ones I remember quicker than cotangent, and evaluated cosine at 1/6 pi, and that would be square root of 3 over 2. Sine of 1/6 is 1/2. Simplifying these fractions, we get square root of 3, and of course 2 divided by -3 gives us -2/3. That is our slope in our tangent line equation. Next, you'll see that I took my x and my y values and substituted in this a value of pi over 6 in both of those. Cosine and sine of those. Cosine gave us the square root of 3 over 2 times 3, which is 3 square roots of 3 over 2. The sine of 1/6 pi is 1/2 times 2 gives us 1. And then those three values each get substituted into our tangent line equation. This is the slope, which we see here, times our x minus our x of a. This is x of a. That's the 3 square roots of 3 divided by 2. And then plus 1. 1 is the y prime of a value. And that's our tangent line equation at t equals 1/6 of pi. Example number 11 asks us to find all points that we have a horizontal or vertical tangent to our curve. So a few steps in this one to get all points. First step would be to find the derivative of x with respect to t, followed by the derivative of y with respect to t. Two simple derivatives for us to find. Then we write that as a fraction and get our dy dx as t squared minus 4 divided by 3t squared minus 6t. Two steps that we're going to do next involve finding the horizontal tangents and our vertical tangents. So starting off with the horizontal. Horizontal, as you recall, was when our slope equals 0, which would be our numerator being 0. And that's our y prime. Y prime equals 0. Factor the t squared minus 4. Solving for this would be zeros at t equals plus or minus 2. Next, we'll look at our denominator. That's when we have our vertical tangents. When this does not exist, the denominator, our x prime equals 0. Factor the 3t out. We'll have 3t times the quantity of t minus 2, which gives us zeros at t equals 0 and t equals 2. Before we go on to our next step to evaluate our horizontal and vertical tangents, we notice right away that we have at t equals 2, a positive 2 for the horizontal, a positive 2 for the vertical, both y prime equals 0 and x prime equals 0. So by definition, we don't have a horizontal or vertical tangent at t equals 0. We're going to have the particle at rest at those points. Okay? So we will eliminate evaluating t equals 2 in our evaluation of finding the points where we're horizontal and vertical. So let's continue on with our horizontal. Horizontal tangency will occur at t equals -2. So since we're asked to find all points, we need to substitute -2 into our x and into our y and get x of -2, y of -2, which would be -8 minus 12, or negative 20 for the x value. Y value will be negative 8/3 plus 8, which is 16/3. So we have a point where the curve will have a horizontal tangent line, and that point is at negative 20, 16/3. For our vertical tangent, we'll do the same thing. We'll substitute in this value of t equals 0 into our x and our y, which actually is pretty simple. When x is 0, or excuse me, when t is 0, our x is 0, and our y is 0. We have 2 points, one where we have a horizontal tangent, and one where we have a vertical tangent. Next, I want to point out to you that sometimes when we're evaluating these, when the particle is at rest, we'll have a 0 in the numerator and denominator, because both of those will be 0, which of course leads us to evaluating a little bit further. To evaluate this, we would actually take the limit as t goes to a of this function and evaluate that. But you can also remember that if we have a 0 divided by 0, L'Hopital will also apply. Either one of those can be used in this case. So let's take a look at this problem a little bit further and evaluate this tangent line when t equals 2. Recall up above, when t equals 2, and again we're looking at the exact same functions here, x of t and y of t are the same. When t equaled 2 of that, we were at rest, which means our dy dx is going to be a 0 divided by 0. So let's go ahead and evaluate that using the two methods we listed up above. First one is I'm going to take the limit as t goes to 2. When I have a 0 divided by 0, we learned first time we saw this, we looked at factoring, and this one did factor. Since it numerator factored to t minus 2 times the quantity of t plus 2, and the denominator factored to 3t times the quantity of t minus 2. And you can see both of those zeros get eliminated. And then when we evaluate this, we just substitute in 2 for t and get 4 in the numerator and 6 in the denominator, which means we have a slope at t equals 2 of 2/3. Go ahead and look at this same problem using L'Hopital. L'Hopital would say I have a 0 divided by 0, so I can take the derivative of the numerator and get 2t. Take the derivative of the denominator, that'll give us 6t minus 6. And then when we substitute in t equals 2, the numerator will be 4, the denominator will be 6, and we simplify to 2/3 also. Either one of those methods is acceptable when you're evaluating our dy dx when we have a 0 divided by 0. So let's make sure we do answer our question. It is, again, write an equation for our tangent line. Now we know what the slope of the curve, either using the limit through the factoring or through L'Hopital. We need 2 more things, and that, of course, is going to be our x of 2 and our y of 2. Substituting in our slope and then evaluating the original x of t function when t equals 2, we get a negative 4. And when we substitute in y equals t equals 2 in our y function, we get negative 16/3, and that's this right here. And of course, when we substitute in negative 4, this should be plus 4 there. Let's take a look at our next equation. And it says, find the tangent line equations to the parametric curve given by x equals this and y equals that. at the point 0, 4. So, same thing we've been doing before. We need to find the derivative of x with respect to t, which will be 5t to the 4th minus 12t squared. Find the derivative of y with respect to t, which will be 2t. Write our dy dx with y prime over x prime. You'll see that we can factor out a t out of both numerator and denominator and simplify this equation to 2 divided by 5t cubed minus 12t. Then I'm going to find the slope of this by substituting in t equals 2. I need to go back a little bit because you might be asking yourself, hey, where in the world did I get this? And I, of course, skipped my step, and that was given this point. This time we weren't given what t equaled. So we need to find out what t equals when we're at the point 0, 4. So first thing we're going to do is just take the x value and evaluate this equation when x equals 0, our x value. So when x equals 0, we'll have 0 equals t to the 5th minus 4t cubed. Factor out the t cubed. We'll get t cubed times the quantity of t squared minus 4, which means t will equal 0 and t will equal plus or minus 2. And that's when x will be 0. We also need to evaluate when y will equal 4. So we're going to set y equal to 4 and evaluate t squared, which obviously gives us when y equals 4, we'll get plus or minus 2 for t. Now you can see, I've noted here, we've got a problem because when y equals 4, t was plus or minus 2. When y equals 0, t was plus or minus 2. But when x equals 0, t also could equal 0. That's going to be a problem for us because you'll see over here, y is not going to equal 4 when t equals 0. So you can see I've noted this. When t equals 0, we will not result in a tangent line since t equals 0 corresponds to the point 0, 0. When I put in 0 into my y function, substitute in t equals 0 in my y function, y is going to equal 0. 0 obviously is not equal to 4. So when t equals 4, we're not at the point 0, 4. We're at the point 0, 0. I've made a quick sketch of that curve that I want to show you to just kind of point out. This curve, x equals t to the 5th minus 4t cubed, and y equals t squared, does this little bow type thing where it goes down and to the right, goes to the origin, and then starts going up and to the right. So we're wanting to find tangent lines at this point here, 0, 4. That's when t equals a -2 and then a +2. But in our analysis, what we found out is as the curve goes this direction, x equals 0 down here at the origin, 0, 0, when t equals 0, which obviously is not the point 0, 4 that we were looking for our tangent lines. Okay? So that's the analysis when we're given a point, not t equals a number. We do have to go back and find t. So now that we have a plus or minus 2, now let's go and substitute those in and write our tangent line equations. So you'll see that I used t equals 2 first, substitute that into our slope equation, get 2 divided by 5 times 2 cubed minus 12 times 2. That gives us 40 minus 24 in the denominator, or 16, which simplifies to 1/8. 1/8 is the slope. We're going at x of 2, which was 0, and y of 2, 4, with a little bit of distributing. Simplifying, we get the equation y equals 1/8 x plus 4. We'll do the same thing with our other t value, -2 and -2. When we substitute in -2, we'll get in the denominator -40 plus 24, which would simplify to 2/16, or excuse me, -2/16, which simplifies to -1/8. I substitute that into our tangent line equation, and we get a second tangent line. Going back to our curve, just to make sure we understand what's going on here. When we look at our curve, remember again, we're traveling in this direction. We go through 0, 4 at t equals -2, and at that point, our tangent line is the equation y equals -1/8 x plus 4. We continue through that point, go through the origin, and then approach and go through that point another time when t equals 2, and that gives us this tangent line of y equals 1/8 x plus 4. Let's take a look at another problem. One other benefit of finding dy dx is to determine when the curve is increasing or decreasing. So when we look at a parametric equation that has x is a function of 5 sine of t and y is the function of 8 sine of t, we should be able to find whether that function is increasing or decreasing at any particular time. In this case, we're going to look at when t equals 3/4 of pi. So, same steps we've been doing before. Find the derivative of each one of those functions. Take those derivatives, write them as a fraction. We'll have the y prime, 8 cosine of t, divided by x prime, 5 cosine of t, which simplifies to 8/5, which is greater than 0, which would say that the curve is increasing. Now, you'll see I've made a quick little note up here. Just doing this might get me in big trouble, because you can see here there could be a case where we have cosine of t equaling 0. We'd have a 0 divided by 0, which would say, hey, we're not increasing or decreasing. We'll have to do another evaluation of that. So just a quick little check here. I want to check to make sure when have a t value of 3/4 of pi, I don't have a 0, which in this case is rather simple because the cosine of 3/4 pi we know is not 0. Therefore, we don't have a 0 divided by 0, and we can say we are indeed increasing. If we did have a 0 divided by 0, then we would say again that the particle is not increasing, or the curve is not increasing or decreasing, but it is at rest. Before we take a look at our next examples, I want to go back and recall what we did when we evaluated dy dx, and we took the second derivative of that. We had to make sure that we remember to use the chain rule, because as you recall, our derivatives need to take into account that y is a function of t and x is a function of t. So we'll take the derivative of dy dx with respect to t, and then we will divide that by dx dt. That should be a division, which would be the same thing as multiplying by its reciprocal, dx dt, or x prime of t. Okay? So again, this is just applying our chain rule, and in words, I've put this here for you, that first of all, we'll take the first derivative of the parametric curve, just like we've done before, y prime divided by x prime, then take the derivative with respect to t of that function, and then don't forget, we divide by dx dt. Dividing by dx dt, remember, is the same thing as multiplying by the reciprocal, or same thing as multiplying by x prime of t. So let's do a quick set of examples on these. First one, you'll see we have two functions here for x and y, and we need to find our second derivative because we're asked to find concavity. Concavity occurs or is shown by our second derivative, and we're looking specifically at when t equals 2. So let's do our steps. Let's find dx dt and dy dt, two simple derivatives. Then write those as a fraction to get our dy dx with y prime of t, the 2t minus 2, divided by x prime of t, 2t plus 9. Second step is to take the derivative with respect to t, and this is a quotient rule problem. You'll see that we have low d high minus high d low, all divided by low squared. And then the important thing that you're going to have to make sure you remember to do is we have to divide by dx dt. And that's going to be the 2t plus 9. 1 over 2t plus 9 is multiplying by the reciprocal. You'll see I distributed my 2's up here. Got 4t plus 18 minus 4t plus 4, all divided by, our denominator is 2t plus 9 cubed, which simplifies to 22 in the numerator because our 4t's cancel each other out. Now our next step is to take this second derivative and substitute in t equals 2 to determine what our sign is here. 22 is the numerator. When we put in 2 in the denominator, we'll get 4 plus 9 cubed, or 13 cubed, which gives us a positive number, telling us that this parametric curve will be concave up when t equals 2. Our next function, or our next example, has two functions. X of t equals t squared minus 5, y of t equals 2 sine of t, and we're going to look for our points of inflection. Concavity, points of inflection, both require us to evaluate our second derivative. You'll see the first steps that I've done. Let's take the derivative with respect to t of x, derivative with respect to t of y, then write them as a fraction with my y prime in the numerator, x prime in the denominator, which simplifies to cosine of t divided by t. Next step is to take the derivative of this with respect to t to find y, our second derivative. Again, we have a fraction with a low d high minus high d low, all divided by low squared. And then, don't forget this guy. We have to divide by our x prime of t, and that's the 2t. With a little simplifying here, we get negative t sine of t minus cosine of t, all divided by 2t cubed. You'll see that they noted to us that we can use our calculator here. We're looking for points of inflection. Remember, with points of inflections occur when our second derivative equals 0 or does not exist, and we have to have a sign change. Since they're allowing us to use the calculator, we're going to go ahead and graph this. We'll find the zeros where we have a sign change. And when I put that in my calculator, notice at t equals 2.793 that I have a sign change. I have a 0 and a sign change. That is not my answer, because you'll see that they ask us not to find when we have a point of inflection, but to find all points of inflection. When we're asked to find a point, we need to answer with an x and a y value. So I'm going to take this t equals 2.793, and I'm going to substitute that in both of my original equations here, my x equation and my y equation. Again, since we're allowed to use our calculator, we would substitute those in. And when I substituted those in, I got an x value of 2.831 and a y value of 0.673. That is the point of inflection of this curve. Okay? Be careful not to evaluate those points in our second derivative or first derivative. Evaluate those when t equals 2.793 in our derivative functions, but make sure you're substituting those back into the original functions. We have one more example here, and in this one we're going back to, let's find where we are concave up and concave down. And in this one, it's not checking at a particular point, it's just saying where will we be concave up, where will be concave down, or we could have cases where we're neither concave up or down. Okay? So you'll see, same process we've done before. Take the derivatives of both of those functions with respect to t. Next, write them as a fraction with the y prime in the numerator, x prime in the denominator. A little bit of simplifying, factored out t out of both of those, wrote the -2 as just -1/2, and now I'm ready to take my second derivative of this. I take the derivative of this with respect to t. The -1/2 is still here. First term will be 75t to the 4th minus 15t squared. And then don't forget, we have to divide by x prime of t, which was our -2t. A little bit of simplifying gives us this equation. Our next steps is to go ahead and find our zeros. So I'm going to take that, set it equal to 0. I can multiply by 4 and get rid of the 1/4. I can factor out the 5t. That leaves us with 7t squared minus 3 as the other factor. T equals 0 will give us 0. And then when the 7t squared minus 3 equals 0, add 3 to both sides, divide by 7, take the square root, and remember, we'll have to have a plus and minus for those. We're back to an old practice that we've used in several chapters before, and that is to use our number line. We can see where we have our 3 zeros, and then I chose the easiest point for me to choose was at t equals 1. I substitute that in here, I get a +5, substitute in 1 in here, I get a positive, positive times a positive, leaves me with a positive, and then I take another look, I see no doubles here, so I can just go positive, negative, positive, negative. And now I can answer my question with concave up when x or dy, our second derivative, is positive. and that's from negative square root of 3/7 to 0, and then again from a positive square root of 3/7 to infinity. Concave down when we are negative, from negative infinity to negative square roots of 3/7, and then again from 0 to a positive square root of 3/7. So that concludes our notes for 15.2. I hope you enjoyed these, and have a good day.